Hey everyone, welcome to video 8-2. In this lesson we are going to be talking about the angle bisector theorem for triangles and its converse, and talk about how to find measures in triangles that are having inscribed circles in them. So just a quick overview here. On page 372, you guys, we're talking about the distance from a point to a line, and that is always drawn as a perpendicular segment from the point to that line. So you can see in the picture here of the angle bisector theorem, this point C, which is on the angle bisector, is drawn at the same distance. CA and CB are the same. So it's equidistant. What we say is equidistant from the sides of the angle. The converse of the angle bisector theorem says that instead of starting with my knowledge about the angles, I know that the distances are the same. And what that does is that it forces the angles themselves to be congruent, and therefore it's an angle bisector. So again, this is the idea of converse, is just taking that logic and reversing the direction. Angle bisector is if a point is on the bisector, then it is equidistant from the sides, and then the converse says if the point is equidistant from the sides, then it's on the bisector. It just kind of flips it around. So what we want to do here is we want to use these two theorems in example 1. Example 1 asks us to find the measure of segment LM, and segment LM is this piece right here. And notice what we're told, or what we can see, is that this ray KM has two congruent angles on either side of it, and that makes it an angle bisector. And so what that means is that the distances JM and LM are equal. And so we're looking for LM to be 12.8 there. For part B, we're told that the distances to begin with in the diagram here, both 74, are drawn from point D to the sides of the angle and at a perpendicular angle there, a 90-degree angle. So that means that this ray BD is the angle bisector. And so if we want to know the measure of angle ABD, now notice that's the top part of this angle right here, given that the measure of angle ABC is 112, ABC being the full angle, what we can say is that that is going to be by the converse, because we're not starting with knowledge about the angles, we're starting about the sides. So converse of the angle bisector theorem. And so that means that the measure of angle ABD is half of the measure of angle ABC, which is going to be half of 112, or 56 degrees. Okay, so let's go to the next page. Page 373 here. We have two your turns you need to work through, finding the measure of QS in number 4 and finding the measure of angle LJM given what you have for initial conditions there. Take a pause in the video and do those two problems before we move on, please. As we move on to the rest of page 373, you guys, with explain 2, just put a little bit of a weight here on constructing the inscribed circle. We're going to do this in class next time we meet, so just wait on that. But an inscribed circle, just as a definitions that you should know, is a circle that is all of the points are inside of a polygon, and that each one of the sides of the polygon is what we call tangent to the circle. It means it touches in only one point. Okay, so if we have, for instance, WXYZ over here, a quadrilateral, we would say that circle C is inscribed inside the quadrilateral. Okay. Now when we're talking a triangle, what we need to do is we need to find the center of the circle inside of the triangle, which is otherwise known as the in-center. And we do that by finding all the angle bisectors. So we're going to do that in class. Like I said, we're actually going to walk through those constructions with your compass and straight edge. But what you need to know is on page 374, And the top of this page is our in-center theorem. So that means that if something is the in-center or the center of the inscribed circle, then again, if you thought about putting that circle inside that triangle, you can see that the radiuses, or the radii, would be segments py, pz, and px. And so if a point is going to be equidistant, as we know, from the sides of any angle, then that means it's on the angle bisector. So P is the point where all the angle bisectors come together, okay? The in-center theorem says the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. Before, in our last two videos, we talked about the circumcenter, which was equidistant from the vertices. This is equidistant from the sides. There's a difference. So let's see what we can do as far as using this theorem to find some missing pieces in our triangles. In example 3, it says JV and KV are angle bisectors of triangle JKL. What we're trying to find is, in part A, the distance from point V to side KL. So point V, if that's the intersection of two angle bisectors, we can assume this is the in-center. We want to know how far is that to side KL. Well, the other distances to the sides are also going to be the same. So V to JL will be the same and V to JK will be the same. And we happen to know that V to JK has a length of 7.3. And so we can assume that all those distances to the sides are 7.3. For part B, we want to know the measure of angle VKL. And again, that's going to be this right side of this angle, VKL. Well, to do that, we have a little bit of math to go through here. So let's just move the page up a little bit. And what we see in part B is that we know, of course, JV is the angle bisector, and it happens to be the angle bisector of angle KJL. And so by the definition of an angle bisector, that means that angle KJL is twice the measure of angle VJL, which is twice the measure 19, which was given to us. And so that's, of course, 38. And so 38 plus the angle that we know, which is the angle JLK of the triangle, which is 106. And that's 144 if we add that all up, plus the measure of angle JKL, this top angle that we have no knowledge of up here, okay? Triangle sum theorem says those three angles have to add up to 180. So I'm going to subtract 144 from each side, and I will get that the measure of angle JKL is 36 degrees. If KV bisects that top angle, JKL, then the measure of VKL is half of 36, or 18 degrees. And there are our two answers for example 3. Question, reflect number 7 says, in part A, is there another distance that you can determine? And remember, we said we knew all the distances to the sides are equivalent. So the answer is yes, of course there is. And that distance would be the distance from our in-center V out to side JL. That would be another distance that we could determine. All right, moving down the page here, we have your turns numbers 8 and 9 that we'd like you to take a look at before you come back to class. And again, make sure you read very carefully. You're told that QX and RX are both angle bisectors, and you need to find a missing measure there. Take a pause in the video and do those two problems before we go on. Finally, you guys, at the top of page 375, in our elaborate number 11 here, is another table we want to fill in as part of your turns for today. I'll just give you a hint that if you're struggling a little bit, to look back at pages 360 and the previous page, 374, to talk about the circumcenter and the in-center theorems and to kind of fill in the blanks. This is a nice table to make sure we kind of have a summary of what each of these theorems says, because they're similar. They're all talking about bisectors of some sort for a triangle, and about equidistance and things like that, but want to make sure that those are all clear. So see what you can look back at. As far as this last row in the table though here, where it talks about location, we will talk about this in class a little bit, and we'll demonstrate where that point could be as far as inside, outside, or on the triangle itself when we're talking about circumcenter or in-center. Okay, so we'll demonstrate that, but fill in the top 2 rows of the table, please, as just a summary of the last 2 sections that you've learned. We'll see you guys next time.